Hi, this is Wen-Jie from Telecom Paris. I'm going to present FingerMapper, mapping finger motions onto virtual arms to enable safe virtual reality interactions in confined spaces. This work is a collaboration between Tseng and Huron from Telecom Paris and Yang from TU Darmstadt. In this video, you can see the user is playing Beat Saber, where they have to cut these cubes with the right color of sabers and also in certain directions. But you can see the user is only using their fingers. So the idea is that we map smaller finger motions onto larger virtual arm motions so that the user can have a smaller interaction space but still maintain their whole body movements in VR. In this paper, we implemented two versions of FingerMapper and conducted two user studies. We found FingerMapper has less physical movements and fatigue, fewer collisions. At the same time, it has a higher perceived safety and reached a similar level of enjoyment and presence in VR. Our motivation is that in virtual reality, we use a lot of whole body movements for the reason of a higher sense of presence or like enjoyment. As the standalone VR devices becomes more prevalent, new contexts emerge in open spaces and also confined spaces, like in car or planes. However, whole body movement is often undesirable, even impossible in confined spaces. We look into previous research to see how we can reduce physical movement and keep virtual whole body movement at the same time. So all VR users has a constraint. It's our maximum arm reach. And early VR research, like Gogo technique by Paparev et al., explored distant interaction. Forstner and Müller extended this concept into AR. The idea here is to interact with out-of-reach objects in VR. However, they didn't tackle the problem of virtual body ownership. So recent research focuses on improving ergonomics while preserving the sense of embodiment. Like ownership by Forstner and Müller, they explore the overhead interaction, and Wenzler et al., they propose nonlinear input amplification to reduce the physical movement, but also keep the virtual body ownership at the same time. These techniques are still on a whole body scale and unavailable for confined spaces. So we got inspired by using extreme limited physical motions, but still keep the full virtual body interaction. Examples are like Gunslinger by Liu et al. They use smaller finger motions to interact with large displays, and Dux et al. They create these neural rehabilitation for post-stroke patients because they have limited arm movements, but in VR, they extrapolate the physical movements so that they can still have the full body motions in VR. So the idea is to move from whole body motions to finger and hand motions so that we can enable virtual interactions in confined spaces. So here we implemented two different mapping functions, attach and direct. So they are both alternatives, and we also design different selection functions. So attach is to create a new mapping using pointing gestures. So we cast a point from our index finger to the maximum unreached surface, and by expanding your index finger, you can reach the points within these maximum unreach. At the same time, we associate finger and arm motions. We inspire by reassociation of body parts, so that this function we call it direct. And in the video, you can see the virtual arm movement is directly associated with your index finger movement. We also design selection functions like thumb button by using your thumb to touch your middle finger knuckle, so that we can select virtual objects in VR. And grab select is another metaphor, like grasping different objects. We chose thumb button for selection because it doesn't disturb movements of the index finger. And by all these interaction design, now we can enable object interactions in VR. Also, like we can enable locomotions. The users can perform like in these climbing examples. And at the same time, we can also reduce large motions like we show at the beginning of the talk. How does FingerMapper perform compared to common VR input techniques like hand tracking and also raycasting? And in the second user study, we asked when using VR in confined spaces, how does FingerMapper and hand tracking affect the user experience? So in the first user study, we compared two R mapping functions, attach and direct, to common VR inputs like hand tracking and raycasting. So the idea here is that FingerMapper can enable these virtual body movements in VR and with a smaller, with reduced physical movements and fatigue, and also the required interaction space. So in the second user study, we deployed FingerMapper and hand tracking into confined spaces. So the participants, they have to play finger grabber and with both techniques, attach and hand tracking. And meanwhile, we measure the sense of presence, enjoyment, and how they perceive safety, like how do they feel safe or do they feel worried about colliding. And we calculate the amount of collisions by browsing through our video footage. So here you can see in FingerMapper, participants, they have a smaller interaction space. And at the same time, if you look at hand tracking, participants sometimes they collide with the windshield or they cross over to the driver's seat, which is dangerous. And also they might collide with a rear mirror, for example. So here we found FingerMapper had a higher perceived safety and fewer collisions. Also, they have a similar level of presence and enjoyment inside a confined VR experience. So so now is the takeaway message of FingerMapper. We want to emphasize that exploring safety might become an important new metric in VR. Because in these new contexts, like in confined spaces or during commute, and also using VR in open space, how VR users perceive safety may become important for future VR experiences. Because you want to be safe, and you don't want to collide with the surroundings, and while you're using VR in different contexts. To conclude, we present the concept and the implementation of FingerMapper that enable larger virtual arm interaction for VR in confined spaces. And we conducted 2 user studies. Our results shows that compared to hand tracking, FingerMapper has less physical movement and fatigue, fewer collisions, and a higher perceived safety. Finally, we present 3 applications to demonstrate how to integrate FingerMapper for different interaction scenarios. So this is the end of my talk. Thank you for your attention, and also I'm happy to take any questions.